We'll start in 1 minute. Today we'll try to cover two sections, 7.1 on angles and section 7.2 on right triangle trigonometry. So first we'll discuss drawing angles. The first definition is a ray. A ray is a directed line segment. It has an endpoint, and then if you want to label 2 points on that ray, such as B and C, the endpoint is where B is. And symbolically, you can represent this ray by writing BC with a rightward arrow above BC. And this indicates that B is the endpoint and the ray passes through the point C. An angle is formed by two rays with a common endpoint. The common endpoint is called the vertex. So if you have two rays with a common endpoint, and I'll label the points A, B, and C. B is the common endpoint, and when you form this angle, the point B is called the vertex, which is what's stated right above. The common endpoint is called the vertex of the angle. Various letters from the Greek and English alphabets are used to represent the measures of angles. And nothing is off limits, but some common Greek letters are alpha, beta, phi, theta. You'll see theta quite a bit. And English alphabet letters can also be used. We'll use the letter T. Sometimes we'll just use capital A, capital B, and so on. Angle creation, begin with two rays, one on top of the other. Fix one ray and rotate the other ray by some specified measure. The fixed ray is called the initial side of the angle, and the rotated ray is called the terminal side. So we'll suppose that we start with two rays, one on top of the other, and then if you rotate one of those counterclockwise, then we create this angle. We started with the initial side. And then where the rotated ray stops is called the terminal side. So that's pretty straightforward. The measure of an angle is the amount of rotation. The definition of a degree, 1 degree is 1/360th of a circular rotation. So if you form an angle by doing one complete circular rotation, then that angle is 360 degrees. Okay, in the xy plane, an angle is in standard position if the vertex is at the origin, the initial side is on the positive x-axis, and the terminal side is in one of the four quadrants. So I have a little bit of space. I'll sketch the xy plane. So we have an x-axis and a y-axis. And an angle is in standard position if the initial side is on the positive x-axis. So this is the initial side in red. And if we rotate counterclockwise, suppose we end up over here in the second quadrant. So this angle, whatever the measure happens to be, let's call it theta for now. So the terminal side in this one ends up in the second quadrant. You might have learned from geometry that the quadrants, the first quadrant is the upper right quadrant, and then moving counterclockwise, the second quadrant is the upper left, and the third quadrant is lower left, and the fourth quadrant is lower right. Okay, an angle with a positive measure is formed by rotating counterclockwise. So in this little diagram that I drew up here, this angle has a positive measure, whatever that is. But you can form angles by moving clockwise, and those measures are negative if you rotate clockwise. And a quadrantal angle is formed when the terminal side is on an axis. So I'll draw a few pictures of quadrantal angles. That ought to be enough. So if we form one angle, I'll just make all of these counterclockwise movements. So if our initial side, if it's in standard form, it has to be on the positive x-axis. And if we move counterclockwise so that the terminal side is perpendicular, then this is an example of a quadrantal angle. And you'll probably recognize that as a 90-degree angle, 90 degrees. Another quadrantal angle, if you move counterclockwise 180 degrees, well, this is also a quadrantal angle because the terminal side is on an axis. And then if in the third case, if we have the initial side on the positive x-axis and rotate 270 degrees so that the terminal side is on the negative y-axis, this is 270 degrees. That's another quadrantal angle. And then if you have one full rotation where the initial side and the terminal side are both on the positive x-axis, then that is a 360-degree rotation. Degrees are nice because most people are pretty familiar with the degree measure of angles. But in many of the applications, it's a lot more convenient to use radians instead of degrees. So we'll discuss radians. The circumference of a circle is capital C, representing the circumference. That's the distance around the circle. And if the radius of the circle is r, then the circumference is 2 times pi times r. You probably know that pi is approximately equal to 3.14, and so 2 times pi is approximately 6.28. So this means that a circle can be subdivided into approximately 6.28 arc lengths, where each of 6 arc lengths is equal in length to the radius. I'll show you a picture of this from the textbook in a couple of minutes. Okay, so a radian, here's the definition. A radian is the measure of a central angle of a circle that intercepts an arc equal in length to the radius of that circle. Okay, so what that means is 2 pi radians is equal to 360 degrees. So a minute or two ago, we saw that one complete rotation of an angle is 360 degrees. So equivalently, that's 2 pi radians. And if you divide both sides of this equation by 2, we get pi radians is equal to 180 degrees. And it turns out that 1 radian is equal to approximately 57.3 degrees. Okay, and an arc length S is the length of the curve along the arc that is subtended by whatever the measure of the angle is. Okay, so this is the picture from the textbook that you have access to. It's the OpenStax Algebra and Trigonometry textbook. Okay, so notice where this radius is, and the measure of the angle where the arc length is equal in distance to the radius, then in radians, this is 1. That's 1 radian. And then each of the other arc lengths have the same measure. Okay, so the idea is this angle formed so that the arc length is the exact same distance as the radius. So if I label the radius r, then that means that the arc length is also r. And whenever that happens, the measure of that central angle in radians is 1. And on the other piece of paper, we saw that 1 radian is approximately 57.3 degrees. So if you're familiar with degree measures, then this looks about right. It looks like it's about 60 degrees. Okay, one other picture, which is essentially what I was showing a second ago. So in this picture, the radius of the circle is r, the arc length is r, and so the radian measure of that angle is 1. That's 1 radian. Okay, moving along. The arc length S is the length of the curve along the arc. So we'll find a relationship here. Let theta radians be the measure of a central angle of a circle with radius r that intercepts an arc with length S. Find the relationship between theta, r, and s. Okay, so I'll draw a central angle. I won't draw the full circle. I'll just draw the sector. The radius is r. Theta is the measure of the central angle in radians, and s is the arc length. Well, this arc length is just a part of the circumference of the full circle. And we know that the full circle has a circumference of 2 times pi times the radius. So this arc length is just a fraction of the circumference. So what fraction is it? Well, we can say that the arc length s is the fraction theta radians divided by 2 pi radians multiplied by the circumference of the circle, 2 times pi times r. Okay, so if theta turned out to be 2 pi, that would mean 1 full rotation. And 2 pi divided by 2 pi is 1, and so the arc length would just be the circumference. But in this picture, theta is smaller than 2 pi, so the fraction of the circumference is determined by dividing theta by 2 pi and then multiplying that by the circumference, and that will give you the arc length for that particular sector. This simplifies. Notice that 2 pi from the numerator divided by 2 pi cancels, so the arc length s is just equal to theta times r, where theta is the measure of the central angle in radians and r is the radius. You might see it written as r times theta instead, but either one is okay. And if you forget this formula, you can always derive it by remembering that an arc length is just a fraction of a circumference. Okay, this also means that theta, if you divide both sides of this equation by r, theta is equal to the arc length divided by the radius. And this agrees with what we were discussing earlier. Remember, if the arc length is the same as the radius, then theta is 1 radian. Okay, so these are some relationships that you'll want to make sure that you know. You can memorize them, or I tend not to memorize these. I just think about what they mean and then derive them on the spot oftentimes. Okay, but keep in mind that this only works when theta is measured in radians. Okay, the radian measure of a circle's central angle is the ratio of the length of the arc subtended by the angle to the radius of the circle. So that's, in words, is what we just did up here. Theta, the central angle theta measured in radians is equal to the arc length s divided by the radius r. Okay, one of the things you'll want to be able to do is convert an angle measured in degrees to radians, and you can do that if you multiply the degree measure by pi divided by 180 degrees. So we'll do that. There are some special angles that you'll want to make sure that you're familiar with. So all of these are special angles: 30 degrees, 45 degrees, 60 degrees. Notice that 30, 45, and 60 degrees, those are in the first quadrant. 90 degrees is a quadrantal angle. And then the next three measures, 120 degrees, 135 degrees, 150 degrees. These are these have terminal sides in the second quadrant, and 180 degrees is a quadrantal angle. It's called the straight angle sometimes. In the next row, 210, 225, and 240 degrees, those are in the third quadrant, the lower left quadrant. 270 degrees is a quadrantal angle. And then finally, 300, 315, 330 degrees, those are in the fourth quadrant, the lower right quadrant, and 360 degrees is quadrantal. Okay, so we want to be able to convert each of those to radian measures. So we just multiply each of those by pi divided by 180. Okay, so 30 degrees, if you multiply that by pi over 180, you get pi over 6. 45, well, let's see, multiplied by pi over 180, that simplifies to pi over 4. 60 degrees is equivalent to pi over 3 radians. 90 degrees is pi over 2. So if you're not familiar with these, make sure that you become familiar with these and know how to convert these special angles from degrees to radians. 120 degrees is 2 pi over 3. 135 degrees, well, that's 3 pi over 4 radians. 150 degrees, that's 5 pi over 6 radians. And 180 degrees is pi radians. 210 degrees. Well, let's see. This one is 30 degrees more than pi. So this is going to be 7 pi over 6. 225 degrees, this is in the third quadrant. This is 5 pi over 4 radians. 240 degrees, this is 4 pi over 3 radians. 270 degrees is 3 pi over 2 radians. 300 degrees. Let's see, this is 5 pi over 3 radians. 315 degrees is 7 pi over 4 radians. 330 degrees is 11 pi over 6. And 360 degrees is 2 pi radians. So as I said, make sure that you become familiar with the radian measures. These are referred to as special angles because of the nice things that happen when we apply the trigonometric functions to those. Okay, finding coterminal angles. Two angles are coterminal if they have the same initial and terminal sides. But the way that can happen, well, there are infinitely many ways that can happen. So in this example, these three angles that measure negative 300 degrees, 60 degrees, and 420 degrees, those are all coterminal. So I'll draw a picture of that. So suppose we have our x and y axes. Let's see, the angles are negative 360 and 420 degrees. Hey, so negative 300, I'll get this on the page here. Something happened. Okay, negative 300, that's counterclockwise. So this is negative 90 to there, negative 180, negative 270, and then 30 more. We're about right here. So this is, that's the negative 300. Notice that this angle right here, the one that's left over, is 60 degrees. So a 60-degree angle is counterclockwise, and it ends at the same place that negative 300 ends. 420, well, that's an angle rotation that makes one full circle and then plus 60. So if you catch that, the first rotation was 360, and then we have 60 more to go, and we end up in the same place as the other two angles. So those are called coterminal angles because they have the same initial side and the same terminal side. Those same three angles measured in radians, negative 300 degrees is negative 5 pi over 3 radians. We already saw that 60 degrees is pi over 3 radians, and 420 degrees is 7 pi over 3 radians. Okay, working with an angle that's inside the 0 degrees to 360 degree range, or in radians from 0 to 2 pi, those are usually less awkward than working with an angle outside of those ranges. So if an angle is given outside of those ranges, then a coterminal equivalent inside those ranges can be found. So to summarize what that paragraph was about, every angle greater than 360 degrees or less than 0 degrees is coterminal with an angle between 0 degrees and 360 degrees. And in radian measure, every angle greater than 2 pi radians or less than 0 radians is coterminal with an angle between 0 radians and 2 pi radians. Okay, the next definition, reference angle. An angle's reference angle is the size of the smallest acute angle formed by the terminal side of the angle and the horizontal axis. So acute angle, an acute angle is between 0 degrees and 90 degrees. So I'll just note that, between 0 degrees and 90 degrees. Equivalently, we could say between 0 radians and pi over 2 radians. Okay, so let's find the reference angles of theta equals 2 pi over 3 and theta equals 7 pi over 6 and theta equals pi over 18. Well, let's see. The angle theta equals 2 pi over 3, that is in the second quadrant. So this is equivalent to 120 degrees, if that helps. So right about here is the 2 pi over 3 radians, or 120 degrees. Okay, so the reference angle is the size of this angle right here. This is an angle less than 90 degrees, and it's formed by the terminal side and the horizontal axis. Okay, so this angle right here is the reference angle. And we can see that the measure of that is 60 degrees, or pi over 3 radians. Okay, so that's called the reference angle. It's just the size measured in a positive quantity. And it's formed by the terminal side and the horizontal axis. Okay, the next angle, theta equals 7 pi over 6. So let's draw a picture of that. So it's positive, so we move counterclockwise. Notice that 7 pi over 6 is bigger than pi. You can think of pi as 6 pi over 6, and this is 7 pi over 6. So it's pi over 6 radians more than pi radians. So it's in the third quadrant. So this is 7 pi over 6 radians. And that's in degree measure, that's equal to 210 degrees. Okay, so the reference angle is the size of this angle. It's the acute angle formed by the terminal side and the horizontal axis. And that is equal to 30 degrees, or pi over 6 degrees. Okay, the angle theta equals pi over 18. If you convert that to degrees, that's just 10 degrees. So this angle is in the first quadrant, pi over 18, or 10 degrees. So any positive angle that's in the first quadrant is its own reference angle. So this is the same as the reference angle. I guess I didn't need to write all of that out, but pi over 18 or 10 degrees. Okay, the next topic, determining the length of an arc. Well, we've already discussed that, but here we encounter it again. Determining the length of an arc. So let theta radians be the measure of a central angle of a circle whose radius is r, such that the intercepted arc length is s. So earlier we found that the radian measure of the central angle is the arc length s divided by the radius r, or equivalently, the arc length s is equal to the radius r times the radian measure of the central angle. Okay, next page. So now we're going to discuss how to find the area of a sector of a circle. So consider a sector of a circle with radius r, whose central angle is theta radians. find the area of the sector? Okay, well, I'll draw a sector without drawing the full circle. So the radius is r, the central angle is theta radians, and the arc length is s. So how are we going to find the area of the sector? I'll refer to the area of the sector whose central angle is theta as a sub theta. It seems like I saw that done once. Well, the area of the sector of the circle is just a fraction of the total area of the complete circle. So what fraction of the total area of the complete circle is it? Well, we did something similar earlier. This angle is theta radians. A full circle has 2 pi radians, and so this sector is just a fraction of the circle. The fraction is theta radians divided by 2 pi radians. So if we multiply this fraction by the area of the complete circle, which is pi r to the second, pi times r to the second, that will give us the area of the sector. And notice that the pi divided by pi cancels. So we can write this as 1/2 theta r squared. Or you might see it written, the area of the sector with central angle theta is 1/2 times the radius squared times theta. Just to note, if theta is 2 pi radians, as we already know, but just an observation that helps, if theta is 2 pi radians, then the complete circle is 1/2 r squared times 2 pi, or pi r to the second. Okay, so this is something that you should memorize, or you should be able to derive it just by thinking about what it means. Okay, linear and angular speed. This is for the motion of a particle or anything on a circular path. The angular speed, as a point moves along a circle of radius r, its angular speed omega is the angular rotation theta per unit time t. So we just say that the angular speed omega is equal to theta radians divided by t. That tells us how many radians per unit of time that point is moving along the circle. The linear speed, as a point moves along a circle of radius r, its linear speed, v, is the distance traveled, which is the arc length f, per unit time t. So as an equation, the linear speed, or you could think of it as the linear velocity, although speed is the absolute value of velocity in general, but the speed or the velocity is the arc length divided by the unit time t. So this relationship, the relationship between the velocity and the angular speed, or the linear speed and the angular speed, is the linear speed is equal to the radius times the angular speed. So how does that work? Well, remember that S, the arc length, is equal to the radius times theta. So if we replace S in this equation with r theta, we get r theta divided by t. Or think of that as r times theta divided by t. But theta divided by t is what the angular speed is. So this is just the radius times the angular speed. So that's where this comes from. Okay, let's consider a clock that has three hands. One is a second hand, one is a minute hand, and the other is an hour hand. So what's the angular speeds? Well, we know that the second hand makes one revolution in 1 minute. So the second hand the angular speed is 2 pi radians per 1 minute. Or you could say 2 pi radians per 60 seconds, but we'll just leave it as 2 pi radians per 1 minute. Okay, what about the minute hand? How long does it take the minute hand to make one revolution? Well, it takes 60 minutes. So we could say that omega, the angular speed for the minute hand, it makes one complete revolution, or 2 pi radians, in 1 hour. Okay, then the hour hand. How long does it take the hour hand to make one complete revolution? Well, it takes 12 hours. So the linear speed for the hour hand is one revolution, 2 pi radians per 12 hours. Or you could write it as pi radians over 6 hours if you want. Okay, let's try this. Find the linear speed of the tip of the minute hand of a clock if the distance from the tip to the center of the clock is 4 inches. Okay, so the velocity is the arc length s divided by t, but we can also write this as the radius multiplied by the angular speed. Well, this formula, v equals r times omega, might be easier, even though the other one works. We're given that r is 4 inches. And we just need to know what the angular velocity of the minute hand is. Well, we found that to be 2 pi radians per hour. So the linear velocity of a minute hand, where the minute hand is 4 inches, is 4 times 2 pi inches per hour. If you can read my writing, or you can write it a little bit more simply, 8 pi inches per hour. That's the linear speed of the minute hand if the radius is 4 inches. Okay, we'll start the section 2 material now. Using right triangles to evaluate trigonometric functions. Okay, a right triangle has one right angle, which is 90 degrees or pi over 2 radians, and 2 acute angles. The acute angles are between 0 degrees and 90 degrees, or between 0 and pi over 2 radians. Okay, so in this part, we'll draw a right triangle. We'll label the measure of one of the acute angles with t. We'll label the hypotenuse. We'll label the side opposite of the angle whose measure is t, and label the side adjacent to the angle whose measure is t. Okay, so a right triangle. I'll label this acute angle as having measure t. The hypotenuse is the longest side of a right triangle. It's always opposite of the right angle. The side opposite of the angle whose measure is t, I'll label that as OPP for opposite. And then the side adjacent to the acute angle whose measure is t, I'll label that ADJ for adjacent. The trigonometric functions are defined in terms of a right triangle like this. But just one more thing to clarify. This opposite side, this represents the length of this side of the right triangle. Adjacent represents the length of this side, and hypotenuse represents the length of the hypotenuse. Okay, so the sine of t is opposite over hypotenuse. That's the definition for the sine of t, the length of the opposite side divided by the length of the hypotenuse. Cosine of t is the length of the adjacent side divided by the length of the hypotenuse. So adjacent divided by hypotenuse. The tangent of t is defined by the length of the opposite side divided by the length of the adjacent side. So tangent of t is opposite over adjacent. Cosecant of t is the reciprocal of sine of t. So cosecant of t is the length of the hypotenuse divided by the length of the opposite side of t. Secant of t, that's the reciprocal of cosine of t. So secant of t is the length of the hypotenuse divided by the adjacent side. And cotangent of t That's the reciprocal of tangent. So cotangent of t is the length of the adjacent side divided by the length of the opposite side. Okay, I already mentioned that there are reciprocal functions. So sine of t and cosecant are reciprocals. Cosine of t and secant of t, those are reciprocals. And then tangent of t and cotangent are also reciprocals. Another way to write that is sine of t is equal to 1 over cosecant of t. Cosine of t is equal to 1 over secant of t. Tangent of t is equal to 1 over cotangent of t. I don't have enough room here, but we could write the other ones. For example, cosecant of t is 1 over sine of t. Secant of t is 1 over cosine of t, and cotangent of t is 1 over tangent of t. But we should know that because of what we know about reciprocals in general. Okay, every right triangle has two acute angles. The right triangle trigonometric functions apply to both of the acute angles. We won't do that here, but if we were to label this other acute angle up here with some other letter, whatever that happens to be, then we could write down the 6 trigonometric functions for that acute angle. Okay, but we'll do an exercise down here. Here it says construct a right triangle with sides having lengths 3, 4, and 5. Label the two acute angles alpha and beta. Write out the 6 trigonometric functions for each acute angle. Okay, so the right triangle has lengths 3, 4, and 5. Whoops, the long side is 5. 3, 4, and 5. It doesn't matter which of the acute angles is labeled what, so I'll just label this one alpha and this one beta. Okay, so using the length 3, 4, and 5, so we'll start with the 6 trigonometric functions involving alpha. So the side, remember, sine of alpha is opposite over hypotenuse. So the side opposite of alpha has length 3, the hypotenuse has length 5. So sine of alpha is 3/5. Cosine of alpha, adjacent to alpha, is the side of length 4, so adjacent over hypotenuse is 4/5. Tangent of alpha, opposite over adjacent, so that's 3/4. And then cosecant of alpha, that's the reciprocal of sine of alpha, so this one's 5/3. Secant of alpha, that's the reciprocal of cosine of alpha, so that's 5/4. And then cotangent of alpha, that's the reciprocal of tangent, so it's 4/3. Okay, now we'll do the same thing for the angle beta. So sine of beta, the side opposite beta has length 4, the hypotenuse is 5. So sine of beta is 4/5. Cosine of beta, see adjacent, 3/5. Tangent of beta, so opposite over hypotenuse. Sorry, opposite over adjacent, 4/3. Cosecant of beta, that's the reciprocal of sine of beta, so that's 5/4. Secant of beta, that's the reciprocal of cosine of beta, so that's 5/3. And then cotangent of beta, that's the reciprocal of tangent of beta, so that's 3/4. Okay, so there's some things here to make sure that you catch, a couple of things. So in this right triangle, the two acute angles, alpha and beta, they add up to 90 degrees, or you could say they add up to pi/2 radians. And notice that from that right triangle, sine of alpha is equal to cosine of beta. And cosine of alpha is equal to sine of beta. Okay, so that's not just a coincidence. That sort of thing happens in every right triangle. Well, the same happens with the other functions. Tangent of alpha is equal to cotangent of beta, and tangent of beta is equal to cotangent of alpha. And then also cosecant of alpha equals the secant of beta, and secant of alpha equals cosecant of beta. So I probably made it more confusing by drawing all those arrows. But we'll see this again in a few minutes. Well, we want to learn how to evaluate trigonometric functions of special angles. You might have noticed that we have to often import what we know from geometry into trigonometry, but that's okay. Here we're going to construct an equilateral triangle, and we'll label the length of each side with 2x. And then we're going to find the height of the triangle in terms of x. Okay, an equilateral triangle is a triangle with 3 sides of equal length. Another thing we know about triangles, if you add up the angle measures of the 3 angles, it has to add up to 180 degrees or pi radians. So in an equilateral triangle, where all 3 sides are equal, each of the three angles is 60 degrees or pi/3 radians. Okay, I'm going to draw the height of the triangle. For any triangle, if you connect a line segment from one vertex to the line that contains the opposite side so that you get a perpendicular in the process, then this blue line segment is called the height of the triangle. And in an equilateral triangle, this height will divide each of those two angles in half. So altogether we had 60 degrees. So each of those two angles is 30 degrees. And you can see that we have two right triangles. The right triangle on the left has angle measures 30 degrees, 60 degrees, and 90 degrees. Yeah, we're supposed to label the lengths of the sides 2 times x. But down here where I've constructed the height of the triangle, I'll label this x and that x. I'll label the height of the triangle with capital A, and we can use the Pythagorean Theorem to find what the measure of A is in terms of x. Okay, so our right triangle, the hypotenuse is 2x. Remember the Pythagorean Theorem, if you square the length of the hypotenuse, so we'll square 2x, that's equal to the sum of the squares of the lengths of the other two legs. So we have the quantity 2x squared equals a squared plus x squared. And we're going to solve for a. The term 2x squared is 4x squared equals a squared plus x squared. And then if we subtract x squared from both sides, we get a squared equals 3x squared. And for now, we're just interested in the positive square root. So a is the positive square root of 3 times x. Okay, so I'll redraw the 30, 60, 90 triangle. 30, 60, 90. So this one is 60 degrees, 30 degrees. The hypotenuse, the hypotenuse is 2x. The vertical side is the square root of 3 times x. And this side down here is just x. So that's supposed to be 60 degrees, not 600. Okay, so let's find sine of 30 degrees. Okay, so here's the Here's the 30-degree angle. So the side opposite is of length x, and the hypotenuse is 2x. So sine of 30 is opposite over hypotenuse, or x over 2x, but the x's cancel, so we get 1/2. So we now know that sine of 30 degrees is equal to 1/2, now and forevermore. 30 degrees in radian form is pi over 6. So from now on, we know that the sine of pi over 6 is 1/2. Hey, let's find cosine of 30 degrees. Cosine of 30 is adjacent over hypotenuse. So this is the square root of 3x over 2x. But x divided by x is 1, so we just get the square root of 3 over 2. And 30 degrees is pi over 6. So cosine of pi over 6 is the square root of 3 over 2. Okay, well, what about tangent of 30? So tangent of 30 is opposite over adjacent. So this is x divided by the square root of 3 times x. The x is canceled, so we just get 1 divided by the square root of 3. So as far as I'm concerned, 1 divided by the square root of 3 is a perfectly fine number. You might see, you'll often see this number with a rational denominator. So you can rationalize the denominator if you multiply the numerator and denominator by the square root of 3, so you get the square root of 3 over 3. But either way is okay with me. And then 30 degrees is pi over 6 radians, so the tangent of pi over 6 is square root of 3 over 3. For now, I will omit the reciprocal functions. I'll just mention the cosecant of 30 degrees, or the cosecant of pi over 6, is equal to 2, because that's the reciprocal of 1/2. Secant of 30 is the reciprocal of cosine of 30. So secant of 30 is 2 divided by the square root of 3. And then cotangent of 30 is the reciprocal of tangent of 30. So cotangent of 30 is the square root of 3. Okay, but I want to find sine, cosine, and tangent of the other acute angle, the 60-degree angle. So let's first find sine of 60. So here's the 60-degree angle, opposite over hypotenuse. So we get the square root of 3x over 2x. The x is canceled, so we get the square root of 3 over 2. Cosine of 60 degrees. So adjacent to the 60-degree angle is x, and the hypotenuse is 2x. So x divided by 2x is 1/2. And then finally, tangent of 60. That's opposite over adjacent. So that's the square root of 3x over x equals the square root of 3. Okay, so the thing that was mentioned earlier, in this right triangle, the two acute angles are 30 degrees and 60 degrees. So note that sine of 30 degrees and cosine of 60 degrees are equal. Also equal are cosine of 30 and sine of 60. Those are equal. Well, we didn't write all of the other angles or the other trigonometric functions, but so that's where I'll stop pointing out those. Okay, so both 30-degree angles and 60-degree angles, those are considered special angles, or in radians, pi over 6 and pi over 3 radians are special angles. Okay, we'll look at another special angle. This time we're going to construct an isosceles right triangle and label the length of each congruent side with x. We'll find the hypotenuse in terms of x. Okay, an isosceles right triangle. Isosceles means two or more sides are congruent. But if it's an isosceles right triangle, then exactly two sides are congruent. And we're going to label the length of each of the two congruent sides with x. And it turns out that in an isosceles right triangle, each of the two acute angles is 45 degrees. Or pi over 4 radians. So I'll remind you, 45 degrees is equivalent to pi over 4 radians. Okay, let's label the hypotenuse C. We'll use the Pythagorean Theorem to find the hypotenuse in terms of x. So the length of the hypotenuse squared, c squared, that's equal to the sum of the squares of the lengths of the two legs. So c squared equals x squared plus x squared. So c squared equals 2x squared. And so the hypotenuse is the square root of 2 times x. Well, pick one of the 45-degree angles or the other, it doesn't matter. Sine of 45 degrees. So the sine of 45 is the length of the opposite side divided by the length of the hypotenuse. So I get x divided by 2 times the square root of x. Well, how do I get rid of the x? Oh, let's see. I labeled this wrong, that's why. The hypotenuse is the square root of 2 times x. So that's why I was confused. Okay, so the sine of 45, I'll rewrite that, is opposite over hypotenuse, or x divided by the square root of 2x. Now the x is canceled nicely, so we just get 1 over the square root of 2. 1 over the square root of 2 is fine. If you want to rationalize the denominator, just multiply by 1 in the form of the square root of 2 over the square root of 2, so you get the square root of 2 over 2. Well, we already know what cosine of 45 is. But we'll go through the motions. Cosine of 45 adjacent over hypotenuse. So x over the square root of 2 times x, or 1 over the square root of 2. Or if you prefer, the square root of 2 over 2. And then the tangent of 45, so opposite over adjacent, x divided by x equals 1. Okay, so the 45-degree angle, or the pi over 4 radian angle, is a special angle. So you'll want to get used to writing the angles in radians. So sine of pi over 4 is the square root of 2 over 2. Cosine of pi over 4 is square root of 2 over 2. And the tangent of pi over 4 equals 1. Okay, the next page. Use equal cofunction of complements. Two acute angles are complementary if their sum is 90 degrees or pi over 2 radians. And as we have seen, the two acute angles of a right triangle are complementary. They add up to 90 degrees or pi over 2 radians. Okay, so let alpha and beta be the measures of the two acute angles in a right triangle. So as has been mentioned, alpha plus beta is 90 degrees. In radians, alpha plus beta is pi over 2 radians. So that means that beta is 90 degrees minus alpha, or beta is pi over 2 minus alpha. Okay, so recall from a couple of minutes ago that if alpha and beta are the measures of the two acute angles in a right triangle, then the sine of alpha equals the cosine of beta, and vice versa. Sine of beta equals cosine of alpha. And it turns out that it's also the case that secant of alpha equals cosecant of beta, and secant of beta equals cosecant of alpha. The tangent of alpha equals cotangent of beta, and the tangent of beta equals cotangent of alpha. So I'll point out the use of the terms for the 6 trigonometric functions are done so in cofunction pairs. There are 3 pairs of cofunctions: sine and cosine, secant and cosecant, tangent and cotangent. So that little observation can be very useful. So here are the cofunction identities. Let t be the measure of an angle in radians. Then cosine of t is equal to the sine of pi over 2 minus t, and vice versa. Sine of t is equal to cosine of pi over 2 minus t. Right? Just go back and look at the examples, and we saw this cofunction relationship taking place. So it also works for the other pairs of cofunctions. The cosecant of t is equal to the secant of pi over 2 minus t, and vice versa. The secant of t is equal to the cosecant of pi over 2 minus t. And this is no doubt monotonous, but I'll go ahead. Tangent of t is equal to cotangent of pi over 2 minus t, and the cotangent of t is equal to the tangent of pi over 2 minus t. Okay, next page. So using right triangle trigonometry to solve problems. Right triangle trigonometry is useful if just one side and one angle of the right triangle are known. So let's work on this exercise. In a right triangle, the shortest side is 5 inches, and one of the acute angles is 60 degrees. Find the lengths of the other 2 sides. Okay, it's a right triangle. We're told that one of the acute angles is 60 degrees. So I'll label this angle 60 degrees. So we automatically know what the other acute angle is. The other acute angle is 30 degrees because in every right triangle, the measures of the two acute angles have to add up to 90 degrees, or pi over 2 radians. Okay, we're told that the shortest side of this right triangle is 5 inches. You probably learned in geometry that in a triangle, the length of the side opposite of the smallest angle is the shortest side. So the 30-degree angle is the smallest angle. So the shortest side has to be the side opposite of the 30-degree angle. And we're supposed to find the lengths of the other two sides. So I'll label the hypotenuse capital H. And I'll label this side, capital T. No particular reason, just I picked T. Well, we know some things about the trig functions and special angles. And we also know the definitions of the trig functions. So I'm going to write down the sine of 30 degrees. That's equal to the length of the side opposite the 30 degrees divided by the hypotenuse. So I have 5 divided by h. But we know what sine of 30 is, sine of 30 degrees. On a previous page, we discovered that the sine of 30 degrees is equal to 1/2. So now I can determine what the hypotenuse is by solving this equation for h. So we can use cross products are equal. If 5 over h equals 1 over 2, then h times 1, which is h, equals 5 times 2, which is 10. And so that will be measured in inches. Okay, so now we know that the hypotenuse is 10 inches. Now we just have one more side to find. Well, we have multiple options. We can use the sine function, the cosine function, or the tangent function to help us find t. So I guess what I'll do is I'll just use 30 degrees again and write the cosine of 30 degrees is equal to the adjacent side, the measure of the adjacent side, t, divided by the length of the hypotenuse. So adjacent divided by hypotenuse is t divided by 10. So if we just multiply both sides of this by 10, we get t equals 10 times cosine of 30 degrees. Earlier, we determined what the cosine of 30 degrees is. Cosine of 30 degrees is the square root of 3 over 2. So t is equal to 10 times the square root of 3 over 2, or 5 times the square root of 3 inches. Okay, as I mentioned, there's more than one way to do that. But we'll do the next example. A right triangle has one angle measuring pi over 6 radians, and its hypotenuse is 30 feet. So find the length of the two sides. Okay, so this time the two short sides are unknown momentarily, and the hypotenuse is 30 feet. Pi over 6 radians, that's equivalent to 30 degrees. So I'll label one angle pi over 6. And the other angle is 60 degrees, but we want to measure it in radians. So let's try our conversion formula. If you want to convert 60 degrees to radians, then multiply 60 degrees by pi over 180 degrees. So 60 goes into 60 once, and 60 goes into 180 3 times. So the 60-degree angle is equivalent to the angle whose measure is pi over 3 radians. So this is pi over 3. And let's just label the two sides A and B. Okay, so I'll use sine of pi over 6 equals b over 30. And so now we can determine what b is. B is equal to 30 times the sine of pi over 6. But the sine of pi over 6 is 1/2. So b is 30 times 1/2, or 15 feet. Okay, now let's just do the sine of pi over 3. The sine of pi over 3 is the length of the opposite side divided by the length of the hypotenuse. So this is equal to a divided by 30. And so a is 30 times sine of pi over 3. We know that the sine of pi over 3 is the square root of 3 over 2. So a is 30 times the square root of 3 over 2, or 15 times the square root of 3 feet. Hey, that's not so bad. A couple of other terms that you'll want to become familiar with are angle of elevation and angle of depression. So if you have an observer who is looking up at something, so he's looking at an object above himself or herself, and then the angle that's formed by the horizontal from the observer, this angle is called the angle of elevation. So just remember, from the observer, there's a horizontal line, and if he's looking up at something, the angle of that point of view is an angle of elevation. Angle of depression. Suppose this time the observer is looking down at something. So he's looking downward at some object. Well, once again, from the observer's point of view, he can look horizontally, and the angle of depression is the angle formed from the horizontal to the line of vision from the observer to the object. So this is what is referred to as the angle of depression. Okay, let's apply that to an exercise. This one says the angle of elevation from a point on the ground to the top of a silo is 41 degrees, and the distance from the point to the base of the silo is 25 feet. So find the height of the silo. So it might help to draw a picture. So here's the silo. And then 25 feet away from the base, this is 25 feet. And then from this point to the top of the silo, we have an angle of elevation of 41 degrees. So we'll label the height of the silo with capital H. Notice that we have a right triangle formed. So it looks like the more convenient trigonometric function to use in this case is the tangent function. The tangent of the 41 degree angle is equal to the length of the opposite side divided by the length of the adjacent side. So tangent of 41 degrees is opposite over adjacent, or h divided by 25. So h is 25 times tangent of 41 degrees. So in our Zoom meeting last week, just the orientation meeting, the question was asked, well, since we can't use calculators, then how do we write answers? Well, this is an example. If you're not allowed to use a calculator, then this is the answer for whatever the height is. You might want to include the units. The units are feet. Sort of a minor detail, unless you're an actual engineer. So that's the exact answer, 25 times the tangent of 41 degrees. Okay, in the remaining minutes, we'll just do some review problems from what we've covered already today until time runs out. We have about 8 minutes left. So in this one, draw the angle negative 150 degrees in standard position. Find the radian measure of negative 150 degrees. And then thirdly, find a coterminal angle of negative 150 degrees that is between 0 degrees and 360 degrees. Okay, so we'll sketch the XY plane. The angle is negative 150 degrees, so that means we move clockwise 150 degrees. So 1/2 of a rotation is 180 degrees. So moving clockwise we're going to stop 30 degrees short of 1/2 of a revolution. So that's negative 150. The problem doesn't ask for it, but the reference angle is 30 degrees. So knowing how to find reference angles is a very useful thing. So I'll just go ahead and mention it. The reference angle is the 30-degree angle. Okay, now find the radian measure. So we want to multiply negative 150 degrees by pi over 180 degrees. So let's see, 30 degrees goes into negative 150 negative 5 times, and it goes into 180 6 times. So this simplifies to negative 5 pi over 6. Okay, what else do we want? Let's see, find a coterminal angle of negative 150 that is between 0 degrees and 360 degrees. Okay, well, a slick way to do that, since negative 150 is outside of the range and it's negative, then if you just add one rotation, 360 degrees, you'll get the answer that you want. So those add up to 210 degrees. And we can verify that. 210 degrees, from standard position, we move counterclockwise, so it's 180 plus 30. Yeah, sure enough, the 210 degree angle and the negative 150 degree angle are coterminal. Okay, the next example, find the angle between 0 and 2 pi radians that is coterminal with 44 pi divided by 9. Well, just note that using the denominator 9, 2 pi radians is equal to 18 pi over 9. So this is a positive number, 44 pi over 9, and it's greater than 2 pi. So to get a coterminal angle between 0 and 2 pi, starting with 44 pi over 9, well, we can subtract 2 pi to see what we get, because that's one full revolution. So let's subtract 18 pi over 9. And we get 26 pi over 9. 26 pi over 9 is still outside of the range between 0 and 2 pi. So we'll subtract another 2 pi from 26 pi over 9. This time, 26 pi over 9 minus 18 pi over 9. And this time we get 8 pi over 9. So 8 pi over 9 is the coterminal angle with 44 pi over 9, and it's between 0 and 2 pi. Oh yeah, let's convert this to degrees. So if you want to convert an angle measured in radians to degrees, then this time you multiply by 180 degrees over pi. So this is going to work out nicely. Pi divided by pi. 9 goes into 9 once and into 180 degrees 20 times. And then we just have 8 times 20 degrees, or 160 degrees. Well, we won't have time to complete this one. I can write down one thing until time runs out. A bike with 24-inch diameter wheels is traveling at 15 miles per hour. Find the angular speed in radians per minute. Also find the wheel's revolutions per minute. Okay, so we're given the linear speed. The linear speed is given. So v is equal to 15 miles per hour. That's the linear speed. And then if you remember that v is equal to the radius times the angular speed, you can determine what the angular speed is. But we don't have time. We're out of time for now. So we might see this practice problem again shortly, like tomorrow maybe. That's all for now.